Today we are going to discuss the MM1 queuing model in more detail. If you recall, in our previous class we have seen what is known as the birth and death process, and while discussing birth and death process we have also discussed MM1 queuing model in some detail, but let us look at this once again. When we talk about MM1, we really tell about MM1 FCFS infinity model. The M is that arrival process is Markovian, second M service process is Markovian, 1 is the number of servers, the FCFS which is called the queue discipline, which is the first come first serve, and the infinity, the first infinity is the system size, that means infinite waiting line, right. There is no restriction on the queuing, anyone who comes can join without any problem, and the last infinity is the population size, that means the input population size, which is also called the calling population, right. So, these are the simplest assumptions MM1 FCFS infinity. In our previous class we have already seen that in a typical MM1 model, the birth and death, the rate diagram will look exactly like this. That means, these are the states 0, 1, 2, then n minus 1, n plus 1. Every time an arrival comes, the lambda, the state changes, right. With every arrival the state changes, but when a person serviced, then the state changes to 0. Now, this service will be always mu, because it is a single server system, right. In higher order system, there will be maybe 2 mu, 3 mu or something like this, depending on the situation. Now, under steady state conditions, we had got certain relationships, and these relationships are very important. So, let us write them down, right. So, steady state MM1 queuing system findings. Right. First of all, P0, we can write this way also, or in a very simple way you can write this. The P0 comes out to be 1 minus rho. What is rho? Rho is the traffic intensity equal to lambda by mu. Something about traffic intensity rho. The traffic intensity rho is basically the busy percentage, right. The rho basically tells that this percentage, that is lambda by mu, suppose it is 70, that means 70% of the time the system is busy, right. So, it can also be called busyness or busy fraction, is a busy fraction of the system, right, that is rho. Now, one thing must be remembered, that when you tell rho equal to lambda by mu, we should remember that this busy fraction lambda by mu will not be always lambda by mu. For MM1 situation, it is lambda by mu, must be remembered. For example, for MMS system, it is lambda by S mu, right. So, it is like the total arrival by total service usually. So, but for all MM1 cases, this lambda by mu is an usual formula, and we shall continue to use them, but this point must be remembered very much. Now, the other results that we have seen in our previous day, that probability n of, that means the n person in the system, is given by rho to the power n, then 1 minus rho. Basically, it is rho to the power n P 0. right. So, this is the probability equations. There are few more results, they are also very important, that expected number in the system. Please recall what is a system. A system means the, let us draw very quickly here, this is the system. The system includes the queue and the service channel. This is system. Must be remembered, arrival is here, the service is here, arrival, service. So, this is a simple diagram, that is there is a system QE, the queue portion and the service channel portion. The people are arriving, people are going out, they are being serviced. The queue plus service channel, the total thing is called system. Now, expected number in the system, what is it? This is called L in the system, mind you, not in queue. That means queue plus the people who is getting serviced. The L is given by the formula rho by 1 minus rho. This is very important, must be remembered, right. And what is the expected number in queue? Expected number in the queue, that is known as LQ. The LQ is given by rho square by 1 minus rho, or in other words it is L minus rho, right. So, these are the formula about L and LQ. Once you know that, but at least you can calculate any one of them. Look here, very simple, you have to just remember this one, P 0 equal to 1 minus rho. You have to remember that P n is obtained by rho to the power n P 0. In simple, what is P 2 then? The P 2 is nothing but rho square 1 minus rho. Why 1 minus rho? Because P 0 equal to 1 minus rho, right. So, P 3 rho cube 1 minus rho. So, this way you can find all the probabilities. What is the, if you have to remember just one formula other than that, that is either you remember L equal to rho by 1 minus rho, or you remember LQ equal to rho square by 1 minus rho, which is nothing but L minus rho, because expected number of people in the service is rho. Why rho? Because the busy period is rho, right. At any point of time it is the rho percentage people who are the time the system is busy. So, in another words you can tell that rho number of people are there in the service. So, how many people are there in the queue? It is L minus rho, right. So, that is LQ. So, this, and then obviously remember Little's formula, L equal to lambda W, LQ equal to lambda WQ, and W equal to WQ plus 1 by mu. So, this formula, if you also remember all these Little's formula, and you can calculate one of the L or LQ or W or WQ, then you can get the others, right. So, you really there is no need to remember all the other formula. You know that W is the expected waiting time in the system, WQ expected waiting time in the queue, right. So, all these formula are going to be very much required in our MM1 queuing system. So, once again quickly the proof is shown that sigma P n equal to 0. So, you can see that P 0 plus sigma rho n P 0 equal to 1. So, P 0 1 plus rho square etc. equal to 1. So, that sum is 1 by 1 minus rho. So, P 0 is 1 minus rho, right. So, this is one calculation that we can do. Rho is called the utilization factor or the traffic intensity. Then let us look at this how L is obtained. right. So, these derivations are to understand really, because the average number of customers in the system is this is an expected value. So, number of people, let us say, is if what is that expected number of people, it could be anything between 0 to n. Probability of 0 is 0 p 0, probability of n is p n. So, since it is an expected number, it should be is the sum of all of these, right. So, it is 0 p 0, 1 p 1, 2 p 2, 3 p 3, 4 p 4, and then finally n p n. So, it is L equal to sum over n equal to 0 to infinity n p n, right. Now, it comes out that you can, since p n equal to rho to the power n p 0, already we have seen. So, we can write down L equal to p 0 sigma n equal to 0 n p n, n rho n, right. So, these n rho n here, how this sum is obtained? Look here, S equal to rho plus 2 rho square plus 3 rho cube plus up to this infinity. If you multiply this S by rho, then you get rho square plus 2 rho cube plus infinity, right. So, and then if you deduct one from the other, then 1 minus rho into S equal to rho plus rho square plus rho cube plus dot 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 infinity. In other words, 1 minus rho multiplied by S equal to rho by 1 minus rho, right. So, what is the sum? The sum S is rho by 1 minus rho square. So, it is a trick that is used to really find the S quickly, right, in a involved manner. Now, S is known, that is that sum. So, now put that sum here, L equal to p 0 rho by 1 minus rho square, but p 0 equal to 1 minus rho. So, you can therefore, 1 minus rho and 1 minus rho from you can remove from numerator and denominator, and therefore, L equal to rho by 1 minus rho, which is lambda by mu minus lambda, but this formula is easy to remember, L equal to rho by 1 minus rho, right. So, how is W? W is L by lambda, W q W minus 1 by mu, L q L lambda W q. So, all of these things can be very easily obtained. You have to simply remember Little's formula, right. So, if you look at the slide once again, so we know L equal to rho by 1 minus rho, L q equal to L minus rho or rho square by 1 minus rho, and you can use all these Little's formula, right. Now, let us look at some problems. The problem is like this. The trucks are, let us take one MM1 problem. The trucks are arriving every 5 minutes on the average. The average loading time is 3 minutes. Assuming exponential inter-arrival or service times, look here, most of the time we shall use what is known as Poisson arrival and exponential service time. But Poisson and exponential distributions, they are interchangeable. Well, how? If the number of arrivals are Poisson, then inter-arrival time is exponential. This point has to be remembered, right. So, sometimes we shall write number of arrivals are Poisson, service time is exponential. Sometimes we shall write the exponential inter-arrival and service times. One has to know that both are same, right. So, find out what is known as expected waiting time of trucks in queue, right. So, in this problem it is an MM1 queue and exponential inter-arrival and service time. What is the rate of arrival? Lambda is 12 per hour, rate of service mu 20 per hour. So, utilization factor rho lambda by mu is 0.6. See, once we get lambda equal to 0.6 utilization factor, then system is busy, because the question was probability that truck has to wait. So, when truck has to wait? Truck has to wait when the system is busy, right. And what is that probability? 0.6. Why? Because utilization factor is 0.6. So, I told you before that utilization factor is nothing but the busy percentage, right. So, if we know that what is the percent of time that a particular truck is to wait, then all you have to do, we have to really find out how much time the system is in busy, or it is equivalent to the utilization period. Now, if we have to find out what is the total waiting time of the truck, the waiting time of the truck W is nothing but L by lambda, that Little's formula we are using, right. So, let us calculate these also here. Let us calculate. In this case, we have known that lambda equal to 12 per hour, mu equal to 20 per hour. So, busy period or traffic intensity .6. So, the total waiting time of a truck W is given by L by lambda, right. Little's formula L equal to lambda W. So, same formula we are using, W equal to L by lambda. What is L? L is rho by 1 minus rho. So, it is 1 by lambda times rho by 1 minus rho, right. So, rho is 0.6, lambda is how much? 12. So, equal to 1 by 12 into 0.6, 1 minus 0.6, right. So, this is coming out to be 0.4, this is 12, so 4.8. So, 0.6 by 4.8 equal to 1 by 8, right. So, we get the total waiting time of a truck is 1/8. What is the unit? Unit is hour, because everything is mentioned in hour. So, W is 1/8 of an hour. Suppose now we have to find out of this 1/8 hour, what is the time that the truck has to wait in the queue. That will be found out as W q. Look, this formula, W q plus 1 by mu equal to W. So, what is W q? Waiting time in the queue, it should be W minus 1 by mu, right. So, we know W which is 1/8 hour, we know mu which is 20. So, it is nothing but 1 by 8 minus 1 by 20. So, 1 by 8 by 1 minus 20, how much it will become? Suppose it can make 40. So, 5 minus 2. So, it is 3 by 40 hours. 3 by 40 hours. So, that is the waiting time in the queue. Now, there is a third question, what is the expected waiting time of trucks in queue per day? Let us look at it here. This is what we have to compute now, expected waiting time of trucks in queue per day. So, what is the expected waiting time of trucks in queue per day? You see, this calculation would require really computing, first of all, what is the waiting time of a queue of a expected waiting time of a given truck is 3 by 40 hours. Now, that is for one truck, right. When we talk about WQ, that is that 3 by 40 hours that we have got, that is for a given truck. That means, every truck has to wait a certain time, that is 3 by 40 hours. So, if that is what happens, then what will happen to all the trucks that come? Now, if we assume a 24 hours working hours and there are 12 per hour, that is the average trucks are coming, then how many trucks are coming in a year, in a particular day, right? See, 24 hours into 12, that many trucks are coming. So, 24 hours into 12, because 12 trucks, that is the arrival rate, 24 is the hours in a day. So, that many trucks are coming and each truck is on the average waiting for 3 by 40 hours, right. So, that is the expected waiting time of trucks in queue per day. So, please remember that WQ which you have got 3 by 40 hours, that is the expected waiting time on a queue of a given truck, but we need to find out expected waiting time of trucks in queue per day. So, in a day there are 24 into 12 trucks that is coming. So, if you multiply all of these, then the total value is obtained, which is coming to approximately 21.6 hours, right. So, this is the problem that we have solved. Let us look at another example. So, in this example it is given that in a bank with a single server, there are 2 chairs for waiting customers. On an average, one customer arrives every 10 minutes and each customer takes 5 minutes for getting served, right. Find the probability that arrival will find at least one chair free. Is it all right? At least one chair free. The probability that an arrival will have to stand and the expected waiting time of a customer in the queue, right. So, in this case again this is an MM1 queue, because there is a single server, but there are 2 chairs for waiting customers, right. So, we are assuming MM1 infinity, that means waiting queue space is infinite. Queue space is infinite, but only 2 chairs. So, what will happen? Supposing if the another person comes, then he will not get a chair. Is it all right? So, let us look here. At any point of time, if the system has got nobody, that means free, you simply go and you can get the service, right. So, this is P0. What is the probability that there is only one person in the system? That means there is a person, the person is getting service, right. So, this is P1, both the chairs are free. There is a third situation, there are 2 persons in the system, one is getting service and the another one is sitting on a chair. So, second chair is free, is it not? So, what is therefore it means? It means that the probability of that an arrival will find at least one chair free is equal to P0 plus P1. See, in this case it is like this, the lambda is given equal to every 10 minutes, customers are arriving every 10 minutes. So, what will be lambda? It will be 1 by 6. What is mu? That and each customer takes 5 minutes, sorry, not 1 by 6, it is customers arrive every 10 minutes. So, lambda equal to 6 and each customer takes 5 minutes for getting service. So, mu equal to 12, right. So, lambda equal to 6 and mu equal to 12, then probability that you get at least one gets at least one chair free equal to P0 plus P1 plus P2, right. So, probability that one gets at least one chair free is P0 plus P1 plus P2. P0 nobody in the system, both chairs free. P1, one person getting service, both chairs free. P2, one person getting service, one person sitting on one chair, second chair free. So, that is what we need to calculate. So, what will be P0? What is rho? First of all, rho equal to lambda by mu equal to 6 by 12 equal to 0.5. What is this value? P0 plus P1 plus P2, this is P0 is 1 minus rho, P1 rho into 1 minus rho, and P2 rho square into 1 minus rho. So, 1 minus 0.5 plus 0.5 into 1 minus 0.5 plus 0.5 square 1 minus 0.5. So, this is how you can calculate 0.5 plus 0.25 plus 0.25 into 0.5, 0.125. So, 0.875. So, probability that one gets at least one chair free comes out to be 0.875. So, that is what is calculation is also shown here. What is the probability that an arrival will have to stand? Very simple, arrival will have to stand when not even one chair will be found. So, the required probability will be 1 minus probability that the arrival finds at least one chair free. So, you see sometimes you have to get it from the other side, right. You have to find probability that an arrival will have to stand, where what happens when there are more than 2 people in the system. That means 1 minus P0 minus P1 minus P2, all right. But P0 plus P1 plus P2 already we have found 0.875. So, deduct it from 1, 0.125, that will be the probability that arrival will have to stand. The third one is very simple, because we already know L equal to rho by 1 minus rho, LQ equal to L minus rho, and expected waiting time of a customer in the queue WQ is LQ by lambda, lambda equal to 6. So, 1 by lambda will be 10 minutes. So, utilization factor rho is 0.5. So, L is 0.5 by rho by 1 minus rho, it comes out to be 1. So, LQ is 0.5. So, WQ will be LQ divided by lambda, but 1 by lambda is 10 minutes. So, it will come to 5 minutes, right. So, that is the example. Let us look at another example. In this case, arrival to an airport with a single runway are Poisson distributed with a rate of 30 per hour. The average time to land an aircraft is 90 seconds and this time is exponentially distributed. Find the utilization of the runway and the steady state parameters L and W, right. So, again a simple problem, lambda is 0.5 per minute, that is 30 per minute, service rate mu 60 by 90, that is 2 by 3 per minute, right, and runway utilization rho lambda by mu half by 2 by 3 comes out to be 75%, and then steady state parameter L rho by 1 minus rho 3 aircrafts, and average waiting time in the system W L by lambda comes out to be 6 minutes. Right. So, as you can see that most of these problems and MM1Q, they are very simple problems really, and you have to really remember all the important formula which we have already shown. Look at this slide one more time, that is P0 equal to 1 minus rho, Pn rho to the power n 1 minus rho, or rho to the power n P0. So, you can therefore easily calculate P1, P2, P3 and all those things. Then L equal to the expected number of in the system rho by 1 minus rho, the LQ is expected number in the queue, that is L minus rho, right, and then the Little's formula. So, if you have this much knowledge, you can calculate almost all the parameters of an MM1Q, only you have to just understand the problem, right. So, that is about it. We shall solve more problems in our next section before we move over to other things, right. So, thank you very much.